Welcome to the another class of design of RC structure. Today we are going to design a dog-legged staircase. Before starting the design, I like to give you an overview about stair and dog-leg staircase. Stairs provide access for the various floors of the building. The stair consists of series of steps called flight with landings at appropriate intervals. Stairways are made up of individual steps. Each step consists of a tread and a riser. The tread is the flat part that you step on, and the riser is the vertical up or down part between each tread in the stairways. Okay, now there are many types of staircase. So, among the types, dogleg staircase is the most economical and common format of staircase. These stairs are arranged with two adjacent flights running parallel with a mid landing. Where space is less, dogleg staircase is generally provided, resulting in economical utilization of available space. In this type of staircase, landing is provided corresponding to the level at which the direction of the flight changes. So, in this lecture, we are going to solve a problem. Actually, we are going to design a dogleg staircase of an office building. So, let's read out the problem. Design a dogleg staircase for an office building in a room measuring 3 meter by 6 meter. This is clear dimension. Floor to floor height is 3.5 meter. The building is a public building liable to overcrowding. Stairs are supported on brick walls of 230 mm thick at the rate of the end of landings. Use M20 concrete and Fe 415 steel. So stair is a very important part of building. This may be a office building, maybe a school building, maybe residential building. So loads and geometrical design for comfort is depending upon the type of building where staircase we have to design, we have to place. Load conditions are different, live loads are different for type depending upon the type of building, and we can select the riser and tread depend upon the type of building and depend upon the crowding, right? So first of all, before RCC design, we have to design the geometrical design of staircase. So let's have a look to the plan of a staircase. You can say this is the plan after geometrical design. We will definitely go through the design, but this is I am showing just because of the rough idea. Here is a plan, 230 mm both side the wall support. After that there are two landings, and in middle there are two flights. So in a floor to floor distance, we have to provide two flights for dogleg staircase. Okay, so let's complete the geometrical design. So proportioning of various dimensions of staircase. Width of staircase is given, that is 3 meter. Considering two flights of dogleg staircase, for a floor we have to definitely consider two flights for dogleg staircase, right? Let's space between two flights 0.3 meter or 300 mm. We can assume that data is not given in question, but we can assume this. as 300 mm or slightly less than that. But in this problem, I am assuming is the space between two flights is 300 mm. Width of each flight total is 3 minus 0.3 meter, that is the space, divided by 2 for each flight, that is equals to 1.35 meter. That this is the width of each flight. Now floor to floor height is given, that is 3.5 meter. So height of each flight is equals to 3.5 meter by 2, that is equals to 1.75 meter. Now assuming the height of riser as 150 mm, which is comfortable for office building which is overcrowding. Okay, so now number of stairs will be height of the flight divided by the riser height, that is 1.75 meter or 1750 mm by 150 mm, that is equals to 11.66, or we may write 12. So we have to provide 12 number of risers. So from the geometry of staircase, we know trade required will be definitely less than, just one less than the riser. So number of trade required is equals to 12 minus 1, that is 11, because the last trade will be the landing. Okay, so let width of each trade is 300 mm. Therefore total going is 300 multiplied by 11, that is equals to therefore total going is 300 into 11, that is equals to 3300 mm or 3.3 meter. Look, now total length available as per question 6 meter, right? Now width of each landing is definitely 6, that is overall length, minus 3.3 the going, so available space, that is available space, by 2 equally divided in two side of the running, that is equals to 1.35 meter or 1350 mm. So let's check out the figure as per the geometric design. This is the plan of this dogleg staircase. All dimensions are written as per the calculation. So total is 6 meter and the width is, length is 6 meter and the width is 3 meter. Okay, so 6000 mm and 3000 mm. Okay. Now run is 3300 mm and total number of trade per flight is 11. So this is marked here 1 2 3 4 5 6 7 8 9 10 11. The 12 number is the landing, mid landing. After that 13 14 15 16 17 18 19 20 21 22 23. After that the floor. Okay, so two landings, the each landing is 1350 mm, which is calculated, you can see here, and width of each landing is also 1350 mm and spacing in between is 300 mm. So this is the geometrical design. After that we have to design the reinforcement for this staircase. So in case of design, we have to design only one flight because another flight is just similar that. So In case of staircase design, dogless staircase design, we have to design only one flight, and one flight is a continuous waste slab. Among the waste slab, the loading system is varying because there are two landing with same load. After that, there are few steps. So this middle portion of the waste slab definitely carry extra load. So in analysis, we will see that uniformly varying load will come in this waste slab. Before starting that, we have to know what is waste slab. Look, waste slab is nothing but the normal slab which is in some inclination angle between two support, mainly used in RCC staircase. Waste slab is raised on the beam to beam, and main stair reinforcement still goes up to the mid depth of the resting beam. Waste slab thickness will depend on the length of the stair run. So let's start the design. Now effective span of flight is equals to center distance of walls. So 6 meter is the clear span plus one bearing, half bearing plus half bearing both side, one bearing, that is 0.23 meter. So 6.23 meter is effective span or 6230 mm. Now thickness of waste slab is, as per thumb rule, L by 20 of span for simply supported slab, that is equals to 6.23 by 20 into 1000, that is equals to 311.5 mm. Now let us take D, effective depth, as 300 mm. We assume that effective depth is 300 mm. Now we have to calculate overall depth. We may provide a clear cover of 25 mm. So 300 plus 25, that is equals to 325 mm, that is the overall depth. Now we have to analyze the loads, which is depends upon overall depth, riser size, tread size, and definitely gamma c, that is unit weight of RCC. So first, weight of waste slab per meter width of flight, okay, that is equals to capital D root over 1 plus capital R square by capital T square root close multiply gamma c. Now capital D is overall depth, R is size of riser, T is size of tread, and gamma c is unit weight of RCC. So D is 0.325 root over 1 plus riser is 150, so 150 square, and by tread is 300, so 300 square into 25, that is equals to 9.1 kilonewton per meter. Now weight of steps. So in this part we have to calculate weight of the steps, that is equals to half into gamma c into R into T by T. Gamma c is unit weight of RCC, R is riser, and T is tread. So this is equals to 25 R by 2, that is equals to 25 into half into 0.15, 0.15 is riser, that is equals to 1.875 kilonewton per meter. So total dead load here is 9.1 plus 1.875, that is equals to 10.975 kilonewton per meter, and live load is given, that is 5 kilonewton per meter square, okay. So total load, that means dead load plus live load, is equals to 10.975 plus 5, that is equals to 15.975 kilonewton per meter. We may write 16 kilonewton per meter square. So factor load WU will be 16 into 1.5, that is load factor given in table number 18 of IS 456 2000, that is equals to 24 kilonewton per meter. Now this is for waste slab of steps, and now for landing. Dead load for landing is 0.325, that is depth of waste slab, into 25, that is unit weight of RCC, into 1, that is width. As we know, for slab design we consider the width as 1 meter beam. Okay, that is equals to 8.125 kilonewton per meter, and live load is 1 into 5 kilonewton per meter square, that is equals to 5 kilonewton per meter width of landing. So total load is dead load plus live load, that is equals to 8.125 plus 5, that is equals to 13.125 kilonewton per meter. So factored load will be 1.5, that is load factor given in table number 18 of IS 456 2000, into that total load 13.125 kilonewton per meter, that is equals to 19.70 kilonewton per meter. So these are the loads. Now loading diagram of stairs shall be as follows. As I said earlier, in this waste slab of staircase there is uniformly varying load applied. Into landing portion the load is 19.7 kilonewton per meter, and in middle portion 24 kilonewton per meter. So now next step is design moment. So you can see here the span length. Total effective span is 6.23 meter. The going portion is 3.3 meter at the middle, and both landing side is 1.465. Why 1.465? Because 1.35 is the length, is the span, landing length, plus half bearing, that is 0.23 by 2, that is equals to 1.465. okay, now design moment. So you can analyze here the reaction at support R suffix A is equals to R suffix B, that is equals to 2 into 19.7 into 1.465 bracket close plus 24 into 3.3 by 2. Okay, this is all right, that is equals to 68.5 kilonewton. Now maximum bending moment at mid span mu is equals to 68.5 into 6.23 by 2, that is total span by 2, minus within third bracket 19.7 into 1.465 into within first bracket 1.465 plus 3.3 by 2 bracket close, third bracket close, minus within bracket 24 into 3.3 by 2 into 3.3 by 4. okay, so mu is equals to 112 kilonewton meter. So this is the moment. So we have to resist that moment and design this staircase. So maximum bending moment allowed for a single reinforced section with Fe 415 bars. Mu limit, actually the formula of mu limit, you know, given I told this in every previous lecture. This the mu limit formula is given in annex G of IS 456 2000. So except FCK BD square, the other full portion, if we calculate for Fe 415 bars, that will be 0.138. So this is 0.138 FCK BD square. So 0.138 into FCK is 20 into 1000, that is B, into D square is 300 square into 1 by 10 to the power 6 to change the unit. Okay, so you can see here the value of mu limit is greater than the moment comes in the section. Hence, this section can be designed as a single reinforced section. Okay. Now, next step is area of reinforcement. So, to find out the reinforcement, AST, area of reinforcement, we know we should use the formula from NSG of IS 456 2000. Mu is equals to 0.87 Fy AST into D within bracket 1 minus AST into Fy by BD to FCK. So, mu is 112 into 10 to the power 6 equals to 0.87 into Fy is 415 into AST, that is unknown, into D, that is effective depth, is 300, we assumed already, within bracket 1 minus AST is unknown into Fy is 415 divided by B is 1000 into D is 300 and FCK is 20. So, from this equation we can find out the value of AST, that is 1117 mm square. So, if you use 16 mm dia bar, then the cross section of the bar will be pi by 4 into 16 square, that is equals to 201 mm square. Okay. So, spacing will be 201 by 1117 into 1000, that is 179 mm. So, we may provide 16 mm dia bar at the rate of 170 mm center to center, because we can deduct the spacing value, right. Now, distribution steel is 0.12% of the area, because this is HYSD bar. So, as per consideration of IS 456 2000 is 0.12% of the area. So, 0.12 by 100 into 1000 into 325. So, 325 is overall depth, that is equals to 390 mm square. So, in distribution steel, if you provide 10 mm dia bar, then the spacing of 10 mm dia bar is equals to pi by 4 into 10 square by 390 into 1000, that is 201 mm. So, we may write 200 mm also. So, provide 10 mm dia bar at 200 mm center to center as distribution steel. So, main reinforcement and distribution reinforcement is already we find out. Now, check for development length. So, the formula for development length you will find out from page number 43 of IS 456 2000. So, LD is equals to 5 into 0.87 Fy by 4 tau BD, that is equals to 5 is dia, that is 16 into 0.87 into Fy is 415 by 4 into tau B is 1.6 into 1.2, that is equals to 752 mm. Therefore, providing 800 mm length of bars at the points where LD is required as shown in figure. So, let us check the final figure. So, this is the figure as per design data. So, as per design data, this is the figure of one flight, and another flight will also the same. So, this is the cross sectional view of the flight. Okay, you can check here the total length. Look, as distribution steel 10 dia bar is given provided at 200 mm center to center, and for main bars 16 mm dia bar at the rate of 170 mm center to center is given. Total overall depth is 350 mm, and the for development length 800 mm length is given, you can see here. Okay. So, this is the ultimate drawing, and here the problem is end. I hope you enjoyed the class. Thank you for listening.